ladies and gents, let's talk about homework series 2 part 1, homework that's going to be given to you in advance of the quiz that you're going to have on October 12th. So if you're watching this, it means you're trying to keep caught up so you don't fall behind. Thank you for doing that. Let's get right into the work. So based on our work today, we have to sketch a couple graphs, f of x and g of x. Note that f of x is given to be the parent function of quadratics. If that's a parent function, we can probably throw down the graph right away because we should know what that graph looks like by memory. Right. So if I'm graphing f of x equals x squared, I can map out a couple points. I know that 0 is going to be the vertex because 0 squared is 0. I know we should have 1 and -1 because 1 and -1 both squared will be 1, and 2 will give us 4. And I'm mapping out just a couple points so we can get a nice sense of what the parabolic shape looks like. And this doesn't have to be perfect. You just have to kind of understand that it looks like that arch kind of thing. It's not actually technically an arch, it just kind of looks that way. But that's going to be our parabolic function. So if we now examine g of x, we have to kind of tune into the differences between the parent function and our new function. And so let's kind of zoom in. So we have a couple things happening. We have this x plus 4 being squared instead of just an x squared. And then we also have this plus 1 on the outside as well. And so now if we kind of think about what that's going to do, since they're both being added, that's both going to incur some kind of shift. And so the question is, how is it shifting? So based on the work you guys did today, and our hopefully we've had a chance to have a discussion by now too, this plus 1 on the outside, this plus 4 will both be shifts, but it shifts in different ways. So plus 1 is going to be a vertical shift. And it's going to be a vertical shift because we're adding to the value of the function. And so we took an x, we did something to it, just like the parent would, and then we're taking that value and adding 1. And so this will affect the y value ultimately. In other words, it's going to be shifting up and down because the y-axis moves up and down. In particular, it's going to be shifting plus 1, which is going to be up. On the other side of things, we have this plus 4. Now the plus 4 is being added to the x before it becomes squared. So if x squared defines a function of quadratics, plus 4 means we're defining what you actually do in that quadratic. In other words, we're going to be affecting the domain. The domain is x. X is going to be horizontal, so this is actually going to inform a horizontal shift. Now this is going to be backwards from what we expect. Like seeing plus 4, our inclination is going to be, well, it's going to be to the right 4. But remember, this has to do a lot with zeros. And so if we add a plus 4 to our x value, the 0 is going to change, but it's going to change in reverse. The 0 of x plus 4 is actually minus 4. And so this is going to actually be a shift left of minus 4. So remember, since we're messing with the domain, we're messing with the zeros, and so it's going to shift to the left, opposite of what the plus 1 to the value of the function is going to do. And so I'm going to copy over this. Let it go. Okay. Oh, there it is. Okay. So I'm going to copy this over just so we have a sense of maybe how this is moving. So if we're going to shift left 4, we can track our vertex over 1, 2, 3, 4, and then we're going to shift up 1. And so if we're going to be tracking points, this 0, 0 moved over 4 and then up 1, so it's not going to be -4, comma 1. All the other points should have shifted as well, so this point that used to be 2, comma 4 now is moving left 4, so this should be at -2. And then it moved up 1, so it should be at 5. And although my parabola isn't perfect, that's pretty darn close to what the point's going to be. And so we can definitely kind of inform our shifting of the graph by simply doing a function analysis or vice versa, as long as we know those rules generally do to a graph. So we move over to the right, question number 2, given that g of x equals x plus 4 squared plus 1, explain why the plus 4 shifts the function left, right, and the 1 shifts the function up and down. Well, I think we kind of talked about that as we were moving it, but it kind of breaks down to this. Like this plus 4 value directly modifies the x, and so the x is our input, x is our domain. Domain is mapped on left and right, the x-axis, and so it's affecting the x, therefore it's going to affect the left and right movement of our graph. This plus 1 at the end modifies the value of the function. It changes the g of x function once you actually chosen an x and squared it. This is going to move the entire value. The value maps to y, therefore it's going to shift up and down. So that's more or less why the addition shifts. It's also why the multiplication doesn't, because we're modifying the value of function by multiplication, not addition. So we'll definitely amplify the graph or squeeze the graph, if you will, if you're multiplying by less than 1, but it shouldn't move the graph. Only addition and subtraction can do that. All right, moving on to question 3. Simplify the following expression as much as possible. That's fair. So one thing we need to notice is that we have a big division problem, and this division problem is separated only by multiplication. This is really great news because what we can do is start canceling out by division and multiplication pieces. And so one thing I can see immediately is I can take a 6 divided by 6. That will ultimately be 1. So this is 1 over 1. That no longer has affected my problem because I just have multiplication and division, so it's essentially canceled. Here I see a 3 that I can take out of a 3 there. Since that's still 3 times x, multiplication is multiplication, those will also cancel. Likewise, I can cancel the x with the x, and that just leaves me with no x's. Again, everything's technically now just 1. This is a multiplication version of canceling. The last thing I see is that we have 2 and 4. Well, 2 goes into 4 2 times. And so on the top, we essentially have 1 times 1 times 2 times 1. And on the bottom, we have 1 times 1 times 1 times 1. Now again, this is why we say all this stuff cancels, because the times 1 stuff doesn't actually matter. 1 divided by 1 is 1 in any cases. And so we really only need to consider this 2, because that's essentially 2 times 1 divided by 1, or just 2. And so when you just deal with multiplication and division, we can cancel by doing that within the problem. Now alternatively, you could have multiplied everything out and then tried to reduce it, but this is ultimately a much faster method. Okay, so explain whether the graph below is continuous. If so, if it is, identify the interval over which the graph is continuous. Now this suggests that continuity doesn't actually have to be complete. We can have partial continuity because I'm indicating that you can have an interval. But either way, let's talk about continuity. So if you recall from Algebra 2, continuity continuous, meaning the same thing, is nothing more than evaluating whether your graph has breaks. Probably the most colloquial way you can think of continuity is if you start at the leftmost part of your graph and you start to trace your graph, can you do so without picking up your pen or pencil? If you can connect all the pieces without picking up your pen or pencil, you can say this is completely continuous. In other words, there are no discontinuities. Discontinuities meaning not continuous, breaks in your graph. So this actually is continuous, and even though the graph continues, we can imply that the continuity should continue. And so the answer to this question is yes. It is continuous, and it's continuous over the interval that includes all the numbers. In other words, it starts at negative infinity and goes to infinity. And we can use bracket notation or interval notation to show that. So in other words, it's completely continuous. All right, let's go to some review. So if you're wondering, yes, this implies that the next quiz we're going to have, you'll still have to make sure you're maintaining old skills. And so finding the zeros by factoring is an old skill that I want to be able to maintain. Now, if we notice here, we're dealing with a cubic equation. A cubic equation with all the parts, meaning our best hope for factoring is going to be by grouping. Recall grouping takes the higher x values as a single group, and then takes the lower x values as another group, and we try to find commonalities in both. So let's get closer here. And so if we take a look at the pink group, I see an x cubed and an x squared. I don't see like coefficients, but I can at least take out an x squared of every term, and that will leave me with x minus 5, because recall x squared times x will give me that x cubed, x squared times negative 5 will give me that negative 5x. We're reverse distributing. Now, our best hope of factoring is to make sure we can take an x minus 5 out of the second term. And so since that is my hope, I'll start there. And so now I need to think about what times x gives me negative 4x. That answer would, of course, be a negative 4. Negative 4 times negative 5 turns out to be 20, so we lucked out. This is not only just factorable, but it's factorable by grouping. Now our job is to continue to extract the zeros. So now we're going to reform our binomial times binomial expression. This will be x squared minus 4, and then we'll combine and just have an x minus 5 because it's common in both. Now in this form, we should be able to extract our zeros fairly painlessly. We have x minus 5 here as a single power term. So x minus 5 will give us, come back here. It will give us a 0 of 5, because 5 minus 5 is 0. Our other two zeros have to come from this expression, so let's do some work over to the side here. I want x squared minus 4 to be 0. This one is factorable, so I can take this to be x minus 2 or x plus 2, because negative 2 times 2 is going to be negative 4, plus 2 minus 2 will be the 0, which is why there's no middle term, meaning our zeros here will be 2 and negative 2. And that is our 3 zeros, because if we recall, with a power of 3 as our polynomial, we do expect 3 zeros. Okay, just a quick note on this one, because it's worth noting. If I didn't want to factor this one, there is an alternative way to find the zeros. So if you think about x squared minus 4 equals 0, now this works only because it's a quadratic. If you had a third power equation, this wouldn't fly because you're going to miss some of your inner zeros. But x squared minus 4, I can just solve this like a regular equation. I can take x squared equals 4, square root both sides, and come up with plus or minus 2. Now if you notice, like these are the same values I came in both, so either method is equally good. Alright, what do we got over here? Distance formula. Okay, remember the distance formula is defined to be just a version of the Pythagorean theorem. Delta x squared plus delta y squared. Change in x squared, change in y squared. You could use that like x2 minus x1 formula. I prefer this one. And so if we're trying to find the distance here, I need to figure out how far apart the x's are. Well, I'm going from 6 to negative 6. That's a distance of 12. And so that will be my a squared. I need change in y. 10 to 26 is a change in what? 16. And so I'll need 16 squared to find my distance. Let me grab a calculator here. 12 squared is, of course, 144. I don't have 16 squared memorized, but 16 squared is 256. And so we're continuing to do our simplification. 256 plus 144 would give me an even 400, which means my distance is going to be a square root of 400, which is just 20. Now again, you could have used a distance equals like the x2 minus x1 squared formula, y2 minus y1 squared formula, and you could have put in those values for x and y. But ultimately, if you accept that this is just Pythagorean theorem, and further that subtracting the x values is just trying to find the difference in the x, and subtracting y values is trying to find difference in the y, then certainly that's an acceptable formula too. So in the end, we get a distance of 20. All right, last section, our ACT prep question. Remember, these are direct ACT given questions, and so this could well models what you're going to see in the test. Let's check out this. We have 2m cubed to the 4th power. So recall your algebraic rules for simplifying exponent properties. If you have a group of exponents taken to a single exponent, in this case 4, you can give that 4 to each of the powers, each of the bases. So this is essentially 2 to the 4th times m to the 3rd, and then taken to the 4th. Now right away, we can look at 2 to the 4th being 16, which means these cannot be the right answer. It's either got to be m to the 7th or m to the 12th. Well, if you look at the m powers as written, we have a power stacked to a power. And so we're either going to add those powers and get 7, or we're going to multiply those powers and get 12. Now if you recall, a power just means that number times itself that many times. Like for example, if you just see like x squared, that just means x times x. X times itself, in this case 2 times. X to the 5th just means x times x times x times x times x. X times itself, in this case 5 times. So with that being said, if we have m to the 3rd to the 4th power, that just means there are 4, because it's the power 4, m cubed. So this is really what it would look like. M cubed, m cubed, m cubed, m cubed. Well, if there are 3 m's here, 3, 3, and 3, that means we have a total of 12 m's. And so in the end, if you have a power stacked to a power, we're just actually multiplying those powers out. And so our answer has to be 6m to the 12th power. So our answer here is actually E. So looking at our last problem, we have for positive integer values x and y, we have x plus y equals 21, and then they want to know what the smallest possible value for the product of x and y happens to be. Now, if you don't know what an integer is, particularly a positive integer, like if you didn't do that study last week, this might turn out to be a pretty daunting task. But if you know what an integer is, and integers are positive whole number values, including 0, then this task actually is easier than it seems. Noticing that they're asking specifically for positive integers, and integers are positive whole numbers including 0. Notice that they're asking strictly for positive ones, And so what this means is we're not going to consider 0 as part of our set, because 0 is neither positive nor is it negative. It's what we call a neutral number. And so the only numbers that can go in for x and y are going to be like 1, 2, 3, 4, 5, 6, 7, counting numbers, whole numbers, numbers that you actually deal with that aren't fractions or decimals. And so the tactic we're going to take is actually to just map out what some of the solutions are to x plus y, and then start testing those in multiplication, because that's what we're asked for in our problem. So we can't start with 0, but we can start with 1. So we have 1 plus 20 equals 21. And so we have 1 times 20 equals 20. Now, that doesn't mean that that's the most efficient value or the smallest value. It's just where we're starting. And so we're going to have to do a little bit more inspection here. Let's move up the value to 2. And so let's get 2 times, in this case, what is it? 2 times 19, or 2 plus 19, excuse me. And that's going to be 21. So now we need to test 2 times 19. So 19 and 19, or 19 times 2 either way, we should get 38. So the number 1 up, and again, that doesn't mean that 20 is the most efficient yet. We don't really have evidence to say anything about that. But we could go to 3 times 18, or 3 plus 18, excuse me. That's going to be 21. So now we need to test 3 times 18. Okay, so 3 times 18 would give us 54. Now we're starting to get some evidence that these numbers are increasing, but we should do just a couple more. 4 plus 17. Let's do 5 plus 16. Now, if these values do not decrease, we can start to assume that the first value is going to be our lowest value. So let's try it. 4 times 17 is going to be 68. And then 5 times 16 is going to be 80. So we can start to believe that maybe this 20 will be our lowest value. But what we should do is continue this list until we get the breaking point. What I mean by that is right now we're taking a smaller number times a larger number, and we're getting 21. We should continue this list, or at least skip ahead in this list, until numbers are about the same, or the second number is now smaller. So if we go all the way to 21, we should test 10 times 11, and of course the next number past that will be 11 times 10. So let's go ahead and check this really fast. So 10 times 11, that's going to be 110. And so we see the steady increase as our factors are moving up the tree, which gives us confidence that 20 is going to be our answer. And so let's go ahead and select 20. So you never want to make any assumptions with these types of problems. You want to make sure that you're having some evidence. That's why it says provide some reason. On the ACT, you're going to have about 60 seconds per problem. And you can easily do this analysis in 60 seconds if your brain is trained to do so. All right. So that's the video here, guys. Thank you very much. I'll see you guys next time.